Hello everyone and welcome to another video. Today I'd like to wrap up our discussion on using the Laplace method to solve linear ordinary differential equations. So in one of our previous videos we discussed the Laplace transform, also known as the forward method or the forward Laplace transform. And then in the video immediately preceding this one we discussed using partial fraction expansion to take a function in the complex Laplace domain and manipulate it into an easier form. Today I'd like to take the last step, which is discussing now the inverse Laplace transform, or sometimes referred to as the reverse, where we basically go from the Laplace domain now back into the time domain where things are useful. So in other words, the goal for today is if we are given a function in the complex S domain, what I want to be able to do now is define the inverse Laplace transform, which would now take this function from the Laplace domain and return now a function in the time domain. Okay, so just to give you an idea of the workflow, if you remember, what we said earlier was we started out with an ordinary differential equation and an input to that system. We basically applied now the Laplace transform to that, or the forward Laplace transform, and after a little bit of manipulation we saw that this allows us to change this ordinary differential equation from a differential equation into algebra, and this returned a complex signal in the Laplace domain S. Then what we did is we did partial fraction expansion or partial fraction decomposition to get us this function x of s in another format. I don't know, maybe we call that x of s prime or something like that. Basically, it's written somewhere nicer. Now, the last step is I want to take this function and we're going to perform now the inverse Laplace transform, right? To get us the signal that we're interested in x of t, right? That was the game plan. Okay, so the whole idea for today is I'd like to discuss just this block, basically performing the inverse Laplace transform. Okay, so like we discussed in the forward Laplace transform, the Laplace transform was just a integral function, right? It was just, this function is basically you throw in something and you perform an integral. Well, that's also the same way that the inverse Laplace transform can be defined. So you could define this function up here. Well, actually, here, tell you what, I'll just leave it up here. Here's the function definition. Why don't I go ahead and we'll say that this operation is basically defined as, again, it's an integral. It's a line integral, actually, in this case. So basically, you take f of s, okay, you multiply by e to the st, and then what you're going to do is you're going to integrate, and it's going to be actually a line integral ds, and you go from over a vertical line, let's write it like this, from gamma minus it up to gamma plus it. Okay, and in this case this integration is done along the vertical line such that the real part of s, that you're integrating over in the complex plane, looks like this, right? So you basically have the real imaginary axis, and then you pick some gamma, right? And this gamma, and you're going to integrate from this direction, right? You're going to go up this vertical line, but you're going to pick this gamma such that it's greater than the real part of all the singularities of f of s, and f of s is bounded by this line. So that is a little bit, okay, that's a fine definition, but as you can kind of see, this is a little cumbersome. Who really wants to do this line integral? Not me, right? If I can avoid it, maybe there's a better way to go about it without having to actually crank through this line integral. So the easier way to do this is we're going to talk about right now. So the concept behind the easier version of the Laplace transform is if you can just manipulate the function into a format that is recognizable, you should be able to go ahead and compute the inverse Laplace transform almost by sight, right? It's like if you had a box of transformers, right, and you pulled out one of the robots, right, and it was Optimus Prime, right, and sure, you could try to figure out what his inverse transformation is, right, to get him into a vehicle mode. You could look at all the joints, you could calculate it, you could try to test fit it, you could do all this kind of stuff, but you all know, everybody knows, right? Optimus Prime, when you see this robot, he turns into a semi-truck, right? Similarly, if you pulled out another guy out of that box, and it was Megatron, right, the leader of the Decepticons, you pull him out, and yeah, again, you could try to perform this cumbersome operation of trying to analyze all of his positions and try to guesstimate or calculate what he would transform into. But again, everybody knows that the original Megatron turns into this very not safe for children, real-looking replica of a Walter P-38 pistol, right? Again, he doesn't turn into this ridiculous thing that Michael Bay decided to cook up here. So in that case, I guess the inverse Laplace transform is kind of ill-defined, because you've got these hacks like Michael Bay kind of destroying what it was actually supposed to be. You know, he really should be ashamed with what he did. But anyway, that's beside the point, right? So the concept now is, basically, I want to take this complex function, either f of s or x of s, it doesn't matter, and I want to manipulate it into a simpler format. So in other words, what I'm going to do is I'm going to take this f of s, right, and I'm going to break it up into a lot of different components, like an f1 of s plus an f2 of s plus yada 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 all the way up to fn of s. Right? Okay, if that's the case, then what I can do is I can take the inverse Laplace transform of f of s, right? This is what we want, and that's just going to be the inverse Laplace transform of each one of these components by themselves, right? Plus all the way down to inverse Laplace transform of fn of s. Right? And the idea is the left-hand side is complicated. It's either, you know, you have to crank through this integral, and that's a big pain in the neck. But the right-hand side, each one of these are going to be easy. So hopefully this is a recognizable form, and we can directly say that that's f1 of t, right? And then similarly, this is also going to be easily recognizable, and this would be f2 of t, right? And all the way down to fn of t. So really, you can see this operation, or these arrows, is really, in our case, the inverse Laplace transform. So the majority of the work actually comes into breaking it up into a recognizable format. The actual inverse Laplace transform operation it's really simple, actually. It's almost just recognizing what it looks like and doing it by sight, or looking it up in an inverse Laplace, or in a Laplace transform table, right? So to hammer this home, let's go through all three examples that we discussed when we were talking about partial fraction expansion, namely, what happens if you have real distinct roots, what happens if you have repeated real roots, and what happens if you have complex conjugate poles. So give me a second to erase the board, and then we're going to do that for each one of those cases. All right, so if you remember, in our previous lecture, we looked at case 1 where you had real distinct poles, or roots, however you want to look at it, right? Okay, so the example we examined there was, we said, all right, you have some complex function f of s, and I think we use s squared plus 8s plus 15 all over s cubed plus 3s squared plus 2s, right? And what we showed last lecture here, during the partial fraction expansion, we went through a lot of effort here to break this thing down into something that's more easily recognizable. So I think we had, this was like 7.5 over s plus a negative 8 over s plus 1 plus 1.5 over s plus 2, right? Okay, so now the inverse Laplace transform is actually really easy. So inverse Laplace transform of f of s, right? I don't want to have to do that line integral on this complicated expression here. Instead, let's look at this. The inverse Laplace transform of 7.5 over s plus inverse Laplace transform of negative 8 over s plus 1 plus inverse Laplace transform of 1.5 over s plus 2. Right? Okay, so again, these constants can come out of them, because again, we need to understand that this inverse Laplace transform operator, it was just an integral, right? So that can easily pop out of the integral, because it's not a function of the variable of integration, which was s in this case, right? So this can now be rewritten as 7.5 times inverse Laplace transform of 1 over s minus 8 inverse Laplace transform of 1 over s plus 1 plus 1.5 times the inverse Laplace transform of 1 over s plus 2. Okay, so now you should look at this, each one of these terms, and really think about this, right? Because we're saying, I want to take the inverse Laplace transform of 1 over s. That's the same thing as asking, what function in time, when I take the forward Laplace transform, would give me 1 over s? Well, that's exactly what we discussed when in our lecture on the forward Laplace transform. You know that a unit step function, right? This function which looks like, you know, it's 0, 0, 0, and then at time equals 0, it pops up and goes up to a value of 1, right? This is what it looks like in the time domain. This function, when you go ahead and you take its Laplace transform, it returns 1 over s. So therefore, the inverse Laplace transform of 1 over s is just the step function, right? And then again, we got to make sure we don't drop this 7.5 term, right? So this is multiplied by 7.5. There you go. Here's the inverse Laplace transform of this whole thing. Just doing it by sight. Similarly, let's do this here. 8 times, again, this thing should look very, very similar, right? We did this exact version of a function in the discussion on the forward Laplace transform. So this is e to the minus 1 times t, right? So again, the concept here was if you had a function which looked like, you know, this, e to the minus 1t, when you take its forward Laplace transform, you get 1 over s plus 1. Therefore, the inverse Laplace transform of 1 over s plus 1 is just e to the minus 1t, and we remember the 8 here. Okay, and I think you figured this out by now. Same thing over here. This is now e to the minus 2t, right? So there you go. We basically have completed it, right? So this is now equal to, again, over here, this is now f of t, right? Because the inverse Laplace transform of f of s is just the function in the time domain. And look at this. This is what we wanted. This is our solution. So we see to get this, it's really the majority of the work is done during the partial fraction expansion phase. And now that makes the actual lookup of this quite easy, okay? All right, let's give me a second to erase the board and let's look at the case 2 that we examined. Actually, you know what? Before I leave that, tell you, before we do that, take a look at this, right? The thing I want to drive home, when you have the case where you have real distinct poles or roots, notice that you end up with a lot of terms that look like e to the minus alpha t, right? And then you have like an e to the minus beta t. You might even have like an e to the minus gamma t, but basically you have exponents, right? So real distinct poles yield a solution in the time domain which is basically a linear combination of exponents, pure exponential terms, okay? So keep that in mind. We're going to come back to that in a couple of minutes. All right, so now if you remember, the case 2 that we looked during our partial fraction expansion discussion was the case of repeated real poles / roots. Okay, so the function that we looked at in this case, f of s, was s squared plus 2s plus 3 all over s plus 1 cubed. Right? And we said that the partial fraction expansion of this was 1 over s plus 1 plus 2 over s plus 1 cubed. Okay? So again, we're just going to go ahead and perform the inverse Laplace transform of this by basically taking the inverse Laplace transform of each one of these terms by themselves, right? Plus 2 times inverse Laplace transform of 1 over s plus 1 cubed. Okay, so again, this one right here, right off the bat, is by inspection, this is an e to the minus 1t. Okay? Plus 2 times, now this is a little bit more complicated. You're going to have to go look this up in the Laplace transform table, but we see that when you have repeated poles, you still are going to get something that looks like, you're still going to get the e to the minus 1t, right? That's this portion here. But then anytime you add a multiple of that, what ends up happening here is you get a term t coming out in the front, okay? And in this case, this is actually, since it's a multiple of 3, I think if you look it up in the table, it's like something like n minus 1, so it's that. And then you have this weird coefficient in the front. Let me put brackets around here so we don't get this messed up. So I think this is 1 over 3 minus 1 factorial. Okay, so again, the 3's you can kind of see come from the multiplicity of this pole here at minus 1. Okay, all right, so in this case, by the time you boil this all down here, I think we end up with this. Again, this term is really easy, e to the minus t plus this whole thing. Actually, this, I think all this boils down to this. This is 1, right? Because this is 2 times 1 over 2 factorial, which is 2. Yeah, so this whole coefficient goes away. So this is 1 times t squared e to the minus t. There you go. Okay, so here's f of t in this case. Okay? So we're kind of done. But again, maybe let's take a moment to sort of think about this, okay? And talk about some interesting things that happen. So again, we had the repeated real poles. So the real poles, again, if you were to plot this sucker out, right, here's on the real imaginary axis, you got poles here, 1, 2, 3. You got 3 poles sitting here at -1. So you still get exponents which decay according to like a -1t, right? So this thing is sitting here on the left half plane, so you still get decaying exponentials. But anytime you have a multiplicity of that pole, it adds a t term in the front. So if you think about this long enough, what does t or t squared or t cubed or anything like that look like? Here's, you know, t squared, t cubed, etc., right? Doesn't this look sort of something like it grows? Right? Depending on the power, right, it grows faster. Here's this thing versus t. But then you multiply it by this other thing, right? Here's e to the -1t, right? And depending on, again, if this was a -1, -2, -3, -80t, right? That depends how fast this thing decays. So what's interesting is you have a term which grows multiplied by a term that decays. And again, you got to ask yourselves the question of which one grows faster or slower. Well, t and t squared and t cubed and all those things, those are actually functions of exponential that are of exponential order. Remember we talked about this way back in the Laplace transform discussion? So eventually, no matter how slow this is, even if it's something like e to the -0.0001t, right? This thing is going to take a while to decay. And then even if you had like a t to the 15th or something like that, this thing blows up initially. Eventually, the exponent is going to squash this t. So the product of this at the end of the day is, yeah, it might grow, but then eventually that exponent is going to win and you're going to come down like this. Okay? So what's interesting about this here is even if you have multiple poles at one location, it's not going to blow up to infinity. It's not going to be a quote-unquote unstable or become unbounded, right? Because as long as it has some kind of component that is in the right hand, a real component that's in the right half, in the left half plane, as long as you're over here, right? This exponent, no matter how slow, will eventually crush the power term. So it will not become unbounded. So again, interesting behavior. We're starting to see some physical intuition linking pole locations to their physical response here. And that's the beauty of this inverse Laplace transform. It really allows us to tie what the pole locations are to what the signal does in the time domain here, right? This is our concrete link between the two. Okay. Give me a second to erase the board and let's go on to our last case of the complex conjugate poles. All right, so for our case 3, this was our complex conjugate poles / roots. Okay, so the function that we looked at in this case was an f of s that looked something like a s minus 1 all over s squared plus 2s plus 2, right? And our partial fraction expansion might be an odd term here, more like completing the squares or just rewriting this. We saw that we could rewrite this thing to look like s minus 1 all over s plus 1 squared plus 1 squared, again, effectively, but just plus 1, right? Maybe let's put the squared in here just for giggles. That's going to make our life a little easier, okay? So again, what you might be tempted to do now is we want to now inverse Laplace transform this to figure out what does this signal look like in the time domain. All over s plus 1 squared plus 1 squared, okay? Now, you come into a little bit of a hiccup right here. If you look in the Laplace transform table, or if you remember when you did in your homework, looking at cosine and sines, you basically notice that the closest thing that matches this format is that there is a Laplace transform or a Laplace signal, something like s plus a all over s plus a squared plus omega squared. okay? And this is basically an exponentially decaying cosine. Will look something like this. Now, the problem here is that if you look at this closely, we have a sign, a SIGN problem. Namely, this is S plus A and S plus A. We have an S minus 1 and an S plus 1. So there is a sign problem here that's not going to allow us to directly take this form and inverse Laplace transform it to an exponentially decaying cosine. We got to get it to look something like this. So we're going to play a little bit of a trick here. What we're going to do here is let's go ahead and in the numerator, let's add 2 and then subtract 2. Okay? You'll agree that does nothing. But now what I'm going to do is I'm going to write a parentheses right here. Okay? And now what you see this does is this is now going to become inverse Laplace transform of S plus 1 minus 2 all over S plus 1 squared plus 1 squared. Everyone agreed I haven't done anything yet, right? Now let's break this up into 2 terms. So we end up with inverse Laplace transform of S plus 1 all over S plus 1 squared plus 1 squared plus the inverse Laplace transform of negative 2 all over S plus 1 squared plus 1 squared. Great. Now this term right here exactly matches the format that we're looking for. Okay, and then over here we just got to do a little bit of juggling, and we're going to pull the negative 2 out, so we have a 1 here matching this 1, and therefore it's going to match another similar format in the inverse Laplace transform table. Long story short, this guy over here, right, this is going to look like an e to the minus t cosine of 1t. And then we got the minus 2, and this is e to the minus t sine of t. Right? So there you go. Here we are. F of t looks like this. And again, it might be worth our time to just think about what does this sort of look like, right? So what this looks like, if, whoops, sorry, plotted that wrong. Well, actually, no, you know what? We probably should have done this. We should put this on the real imaginary axis because I wanted to look at the poles, the complex conjugate poles of this. So I think that was a pole of, it was over here, like minus 1 and minus 1, right? I think the poles were negative 1 plus or minus I, okay? So what these poles do is you see when they leave the real axis, you start to get sinusoidal terms, okay? And depending on how far away you move from the real axis, the angular frequency of the sine and the cosine wave are going to increase. And again, depending on which direction you move here, that's going to change now the rate of exponential decay. So again, here's a nice mapping between what the poles look like and what the actual function in the time domain looks like. So this is so worth it that actually, tell you what, give me a second eraser board and let's plot this out and summarize this in a larger picture. All right, so to summarize, right, let's talk about maybe make a table here where we've got the roots / poles on one side of the table, and then let's talk about what they sort of look like in the time domain. So let's call this maybe time domain signal. Okay, so what I'm getting at here is, again, we had this case 1, right? Case 1 was real distinct poles. Right? And we saw what that did is that yielded terms that looked something like e to the minus at or something like that. Okay? And then the next row of our table here in case 2, where you had repeated real poles, right? We saw what that ended up looking like is you still had the e to the minus at, but then there was this coefficient in the front. It was something like 1 over n minus 1 factorial times t to the n minus 1, right? So you had a growing term multiplied by an exponential term, but we saw that eventually at the end of the day this thing died away, right? As long as the a was positive, okay? And now in our case 3, which was our complex conjugates, right? We saw that yielded terms that looked like combinations of exponentially decaying e to the minus at times some cosine omega t, right? and then plus, some other, e to the minus at sine omega t. So basically you get these sinusoidal behaviors. So maybe let's go ahead and over on this side of the board, draw ourselves a big real imaginary axis. Draw a big complex plane, okay? So let's just start talking about case 1. So case 1, if you had a pole that was right here, okay? I want to just draw maybe what does the corresponding signal associated with this pole look like in the time domain. So here's my f of t. Right? And we saw that, okay, if you're sitting out here, this looks like e to the minus at. So this thing is going to look like this, right? Now, what happens if you go further out? Okay, out here, you're going to get, again, we'll draw ourselves something that looks like, I want to see what the signal that is associated with this pole is. Now, since the pole is much further in the left half plane, that A is going to be bigger. So instead of this being like e to the 1t, this is like e to the negative 1t. This is going to be like e to the negative 10t, right? If this was at minus 1 and this was at minus 10, right? So this is just going to look like it decays much faster, but it still is going to decay, right? Contrast that if we had to happen to cross this imaginary axis. Let's say you had a pole right here at like positive 1. What again does the signal of f of t versus t look like? Well, in this case, now this looks like an e to the positive 1t. So this looks like it just kind of grows exponentially. It's going to blow up, right? And again, let's look at one way out here. Let's say, how about positive 10? In this case, this is going to look like an e to the positive 10t, which also blows up, but blows up a lot faster, right? And again, if you had, we could repeat this game like if you had multiplicity of these poles, right? You now end up in case 2 where you now still have this growing portion, but it's still squashed by the exponent. So really, I don't want to clutter this picture up too much, but maybe let's draw one of them just to see what it would look like. So again, if you had a multiple poles, let's put 2 of them here. I'm going to draw both of them over here at minus 1, right? You would end up with some term here that looked like e to the t times e to the minus 1t. So this might look like, it starts growing and then it's going to start decaying eventually, right? Okay, now let's come here to case 3. Case 3 here is if you had complex conjugate poles. So now let's come off the axis here. So let's make a complex conjugate pair like out here or out here, right? What is the signal that's associated with this pair? Well, again, what we'd see is that you're going to get things that look like these exponentially decaying terms, but there's going to be a sine and cosine wave associated with it. So again, the exponentially decaying portion might look like this, right? And now, on top of this, you have some sine wave. Okay? And similarly down here. Right? Now, what happens if you push it further along, like out on the, away from the real axis? So you have a more imaginary component. So let's put one out here. Here's a pole. Okay? So we're going to see that out here, the decay envelope, this e to the at is the same. So this decay envelope, I'm going to try to draw it in a similar fashion. Okay? But the term that's going to increase is this omega. So now it's still going to decay like this, but it's going to go a lot faster. The angular frequency is going to be like this. Right? Does that make sense? And similarly, if you push now this way, if you increase the real component but keep the imaginary part the same, right? Let's draw it out here. What that is going to look like is, okay, now the angular frequency omega is going to be the same, but the decay envelope is going to be much faster. So I'm going to try to draw it. Okay, that was maybe, I might have butchered it, but I think you get the idea, okay? And then lastly, let's think about what happens if you flip over and you come over to this half of the complex plane, okay? We see that now if you put one right here, the signal, what it's going to look like, right, is now it's going to be an e to the positive 1t times sine omega t. So again, the angular frequency is going to be the same, but this decay envelope is not going to be a decay envelope anymore. It's going to be an explosion envelope, right? It's going to look like this, but the angular frequency as this thing blows up is going to be similar. And maybe since we're on a roll, let's do one more. Like how about out here? Okay, So again, similar story. This thing is just going to blow up much faster, but the angular frequency is going to be the same. Okay, so this is fascinating here because this, now that we understand the inverse Laplace transform, we can see exactly how the behavior of where the poles are located in the complex plane, how does that actually influence the physical behavior of the signal in the time domain, right? Because that's really what we care about. I want to know, what does the signal do in the time domain? Does it become unbounded? Does it stay bounded, but does it oscillate? Et cetera, right? So this here, I can't stress it enough. This is really exciting because the inverse Laplace transform is giving us the mechanism to understand the concrete link between the pole locations and the physical behavior of the system in the time domain. Okay, so with that being said, let's look at that a final example of how we can finally apply this to solving a linear ordinary differential equation. All right, so let's look back at the example we looked at in our Laplace transform discussion, which was our mass spring damper. Right, and just to refresh your memory, this was your classical linear ordinary differential equation system, right? It's just a mass hooked up to a wall with a spring with spring constant K and through a linear damper with damping coefficient B. And what we were going to do with this brick here is we were going to apply a force, some force U of t on it, and we're going to measure the deflection x of t of this block. Okay, now what we had done earlier in our Laplace transform discussion, so I won't do it here, is we got equations of motion, right, of this thing in the time domain. We saw that it was a linear second order differential equation. I think we also chose a bunch of inputs. Like I think we said U of t was going to be just a unit step. So we're just going to bam hit this thing with 1 Newton of force. And I think we also put initial conditions on this block. So x0, the initial position was -2 meters. So it started over here on the left, and x dot at time 0 was +3 meters per second. So it started over here on the left, but it was traveling to the right at 3 meters a second. So here was the setup of the problem. And I think what we did last time, or sorry, in the lecture discussing the Laplace transform, the forward Laplace transform, is we showed how you could take this thing and get its ordinary differential equations of motion, which turned out to be a set of linear second order ODE. And basically we Laplace transformed that thing and got it into the signal. We found out what the signal was in the Laplace domain, x of s, and I think it looked like this. Let me just write 1 over ms minus 2s plus 3 minus 2b over m all over s squared plus b over m s plus k over m. There, okay. This was what the system did in response to this unit step input with these initial conditions. This is what it looked like. Now, let's make our lives a little bit easier. Let's go ahead and also choose a mass of, a mass of 1, a spring constant of 2, and a damping ratio, damping coefficient of 3. So let's just jam these into here and clean this up and rewrite it in the format that's helpful for us, basically a numerator polynomial over a denominator polynomial. So if you do that, you can show that, all right, here's what the brick does in the Laplace domain. So this is 2s squared plus, nope, sorry, this is a minus 3s plus 1 all over s cubed plus 3s squared plus 2s. There we go. Okay? So again, here, that's where we left it. That's where we stopped, okay? Now, let's apply our techniques of the partial fraction expansion and the inverse Laplace transform to get this thing in the time domain, because I want to know what is the x of t, right? Where is the block at any given time, okay? So, first thing we got to do, if you remember from partial fraction expansion here, is find the roots, or the poles. Right, so basically solve the denominator here, and we're going to see that you got poles here at s is equal to 0, s is equal to -1, and s is equal to -2. So again, to plot this guy on the real imaginary axis, you got a pole here, here, here. 0, -1, -2. So in this case, none of them are repeated, so we are in the situation of what? Of case 1, where you have real distinct poles. Okay, so what that meant is that, okay, the partial fraction expansion associated with this thing was going to be an a1 over s plus an a2 over s plus 1 plus an a3 over s plus 2, right? And now go ahead, do your coefficient method, your multiplication method, whatever you like. We already discussed this all in the partial fraction expansion lecture, how to get your A1, A2, and A3. And I think what you're going to end up with is, if you do that, you end up with, here, you get an A1 of positive 1/2, an A2 of -2, and an A3 of -1/2. Okay, so the function x of s, right, can be rewritten as what? We got 1/2 over s minus 2 over s plus 1 plus, whoops, sorry, I guess a minus 1/2 over s plus 2, right? Okay, so now I want to inverse Laplace transform this signal to get it into the time domain. So that just means I got to inverse Laplace transform each one of these guys. And tell you what, I'm going to pull this constant out. So this is going to be 1/2 inverse Laplace transform of 1 over s minus 2 times inverse Laplace transform of 1 over s plus 1 minus 1/2 inverse Laplace transform of 1 over s plus 2. Right? And we're basically home free, because if you look at this, these are all easily recognizable Laplace functions, right? So this we know is just a unit step, right? Minus 2 times this inverse Laplace transform is just e to the minus 1t, right? And then we end up with this one, which is e to the minus 2t, right? So here we go. We're done. This is x of t. Here's what the block looks like, or what it does. Okay, and you know what? Let's jump over to Mathematica now to just to double check. I'm going to show you how to use a function to check to make sure you did the inverse Laplace transform correctly. And let's also check that this function that we obtained here obeys the initial conditions of the problem. Namely, when it is evaluated at time equals 0, this thing better equal -2. And when I take its derivative and then plug in 0, it better equal 3, right? So let's do that. Let's jump over to Mathematica and see if we got this to work.
All right, so the first thing to do is let's go ahead and input our solution. So I think we said that x of t was 1/2 minus 2e to the minus t minus 1/2 e to the minus 2t. Okay, so this was our solution that we obtained via quote-unquote manual techniques. So now what we want to do is let's go ahead and check this against Mathematica's inverse Laplace transform. So they have an inverse Laplace transform, just like they have a Laplace transform function, which is super helpful for doing this symbolically. So the first thing we need to do is let's define our signal in the Laplace domain x of s. So real quick, I did screw up on the board. I wrote 2s squared minus 3s plus 1 all over s cubed plus 3s squared plus 2s. That's what I wrote on the board. I missed the minus sign. It's supposed to be negative 2s squared. So this is how to make everything consistent. And I think I did call that out in the video just beforehand, but hopefully you picked that up now. So this is really what the function looks like in the Laplace domain. So again, to perform the inverse Laplace transform to get this into the time domain, all you got to do is call inverse Laplace transform, pass it the function or the complex, the complex function in the S domain, and say, I want to go from the S domain to the time domain. That's literally it. Let's call this maybe result, let's call it x check of t, and shift enter, and you see we basically get the same thing. Let's just double check that. X of t equals x check of t. And yeah, we get a true. So here is another great way to check that you're doing the whole partial fractions expansion inverse Laplace transform correctly, is Mathematica's got an inverse Laplace transform function. Great. So now, last thing to do here is let's go ahead and check that this satisfies initial conditions, right? So what that means is x at time 0, whoops, let me just write 0, this had better equal, there we are, -2. So that worked out. Let's also go ahead and look at what is the derivative x of t with respect to t. So this term right here is x dot. I need to look at when x dot at time equals 0. So that's the shorthand way to do that. And let's go ahead and shift enter that. And yay, check it out. It matches. So the initial position is -2 and the initial velocity here is +3. So just for giggles, last thing to maybe do is let's go ahead and plot this function. So plot x of t from time t going from 0 to, I don't know, 10 seconds, just so we can see what the block looks like. And again, this is what we've got. And maybe it seems to have cut something off, so let's change the plot. Nope, not plot style. I want plot range to all. And there we go. So indeed, we start off at the correct initial condition. We go up to the appropriate value. And again, if you think about this long enough, this thing was a mass hooked up to a spring of constant 2 and applying a unit step of 1 Newton. So really, at steady state, at time equals infinity, right, the system should be sitting there where the spring force should equal the 1 Newton force that we're applying. And that's exactly what happens, right? Because look, it goes to a steady value of ½ meter. So ½ meter times the spring constant of 2 equals 1 Newton, which is exactly what we put on the block. So again, this looks totally reasonable. And again, the nice thing about having the signal in the time domain is now we can understand its behavior. So we see there's no oscillations. The block is not going to overshoot past this ½ meter and hit that bus full of nuns on the far side, right? It's just going to slowly go up here to ½ meter. So this is great. So with that being said, let's jump back over the board for some closing thoughts.
All right, so what I want to do real quick before we close and wrap things up here is let's look at an example, or actually it's the same example we were looking at earlier, where you have a quote-unquote improper complex function. That was where the order of the numerator was equal or greater than the order of the denominator. I want to keep this picture up because let's keep this in mind. We're going to see that it has some ties to a physical system. So if you remember in our discussion earlier, in one of our previous lectures, we said, all right, what if you had a function f of s, which looked like s cubed plus 5s squared plus 9s plus 7 all over s plus 1, s plus 2, right? Okay, so in this case, you got a numerator of order 3, you got a denominator of order 2. What happens here? And what I want to think about is, instead of this being f of s, what if this was x of s, right? The position of the block here in the Laplace domain, right? What if it looked like this? So in our previous discussion on partial fraction expansion, we showed that through synthetic division and your normal partial fraction expansion techniques, you could rewrite this whole thing to look like s plus 2 plus 2 over s plus 1 minus 1 over s plus 2. Okay? Now, to get the position of the block x of t in the time domain, right, all you have to do is inverse Laplace transform this thing, right, which is the same thing as inverse Laplace transforming each one of these simpler terms, right? 2 plus inverse Laplace transform of 2 over s plus 1 plus inverse Laplace transform of negative 1 over s plus 2. Okay? So what's going on here that makes this interesting is these two terms are no problem. These look like what we've done before, right? This comes out to be what? Minus e to the negative 2t. And this one comes out to be what? 2e to the minus t, right? Those look totally fine, right? The block can have exponential terms. Now, what the heck is going on over here? When you inverse Laplace transform this, right? What is the inverse Laplace transform of, well, I guess tell you what, let's make this even easier. Let's move the 2 outside, right? Okay, what is the inverse Laplace transform of just 1? That's this impulse function, right? And then you got to multiply it by 2. So this signal is a little bit ridiculous to being describing the position of the block. The block can't really have an impulse. That's like this instantaneous like jump up and then jump back, right? And this is even worse, right? This, remember we talked about earlier, when you see an s in the Laplace domain, that should be a time derivative in the time domain. So this is almost like it's what? It's the ddt of an impulse. Right? And this is even more ridiculous. Like, what the heck does this mean? Like, if you tried to plot this thing, right? This is now claiming to be the position of the block. You know, t versus x of t. What the heck is going on here at time equals 0? There's this weird impulse and then a time derivative of an impulse. So like this thing does something crazy and then it looks like an e to the minus something. So again, this illustrates why you're not going to really see these improper complex functions if the signal corresponds to an actual physical signal in a real system, because you can't get these things, they're not real time domain signals, right? They're these mathematical, like, fictional signals, okay? So that's why, for the most part, you are going to see only strictly proper, or actually even better than that, is you're going to have signals where the order of the denominator is strictly greater than the order of the numerator, right? To avoid this kind of ambiguity here, right? Okay, so tell you what, give me a second to erase the board, and I want to summarize our approach of using the Laplace transform method for ODEs. All right, so what I'd like to do right now is just summarize how we can now use the Laplace method to solve linear ordinary differential equations, right? And we talked about this earlier, but now I think we finally see the entire roadmap, and I'd just like to summarize this and write it down again, okay? So what we're doing here is you start with the ODE, right? This is of the form something like x dot of t is equal to some f of x u of t, right? And usually this f is going to be linear in x and u, okay? So you can have a linear ordinary differential equation, right? The next thing here is the input u of t is given, right? So you know what external inputs you're subjecting your system to, okay? Once you do that, we saw now that the way to take this ordinary differential equation, basically it's a differential equation, and make it into something easier is you're going to basically apply the Laplace transform. Okay? And what that's going to do is it's going to obtain it's going to allow you to then use algebraic techniques instead of differential equation techniques to solve for x of s, right? Because what this is going to do is it's going to take all those derivatives and it's going to turn them into s's in the Laplace domain. So step 4 then is going to be you solve using algebraic techniques. Right? And then finally, the last step of the process, which we just discovered here or discussed, was you're going to apply the inverse Laplace transform on x of s, right, to get what you're really looking for, which is the signal of interest in the time domain, right? And really, we saw that step 5, it's really kind of 2 steps, right? One of them is doing the partial fraction expansion on x of s, which you obtain up here. Maybe we should have written this up here. You apply algebraic techniques to get x of s, right? So you partial fraction expansion this thing, and then you just look it up, its inverse Laplace transform in a table, right? So at this point, I think this is pretty helpful because now we should understand the entire workflow of how to take any linear ordinary differential equation, as long as you know the input, and the input is a reasonable input which has a Laplace transform, and how you can go ahead and use algebraic techniques and the Laplace method to basically solve this differential equation. So this is a very powerful technique. I like it because it's very straightforward. It's very formulaic, right? It's just turn the crank, and as long as you know each step here, there isn't a whole lot of guessing involved. We're going to take a look at some other techniques, like traditional ways to solve ordinary differential equations, and we'll see that there's a little bit of a difference, and I actually prefer this technique a lot more. Okay, so with that being said, I hope you enjoyed the discussion today. If so, I really would like to encourage you to subscribe and hit the like button, because subscribing really does actually help me continue making these videos. And with that being said, I hope you'll join us at our next discussion, where we're going to continue our exploration of ordinary differential equations. We're going to look at some traditional ways to solve ordinary differential equations, so we have a way that we can compare and contrast the Laplace technique. So until I catch you at one of those other videos, I'll talk to you later. Bye.